Okay, kids, so this is the gas law lecture number 2, kind of taking the first one and then expanding on that. And now you can do some kind of clever things to analyze some data. So let's start with something that doesn't seem to relate to this, but yet it will. So, and this is this idea of molar mass. So let's just kind of a Chem 1 thing, I know, but we'll get there. So remember, molar mass is technically grams per mole, which you can express as mass divided by molar mass, which sounds odd, but if you look at what happens, so let's say that you have 2 grams of helium, okay? So if we take 2 grams of helium and divide that by the molar mass, that's 4 grams per mole. Well, that works out to a half of mole, okay? So we're going to take advantage of this idea later on. So we're going to go with the ideal gas law that PV equals nRT, and we're just going to solve this thing for pressure. So for moles, okay, so this is going to be huge. So we're going to come in here and say, okay, well, moles, which is what we just showed up here, is grams divided by grams per mole. So if I take mass and divide it by the molar mass, that gets me the number of moles, okay? So kind of a clever little trick right there in terms of the mathematics. So what we're going to do then is we're going to separate this out, and remembering that density, and those come back to this little thing over here. So density, remember, is mass divided by volume, which in a chemistry class is grams per liter. If you're in a physics class, that's kilograms per cubic meter, but since we're in chemistry, it's grams per liter. So all I did was that I rearranged this just a little bit. So I said, okay, if I look at this in terms of taking this mass here and this volume here, okay, I can combine that here, okay, so that's mass per volume, so I pulled that out. And then this grams per mole, right, is divided, so I'm going to move that down below, and then I've got my RT. Now, if you remember from over here, we said that density was mass per unit of volume. So I'm just going to take and substitute density into here. And then grams per mole, remember, was the same as our molar mass. So I've got pressure equals density times RT divided by molar mass. So that's dirt, okay, divided by the molar mass. And then if I solve for molar mass, I've got dirt divided by RT over pressure. Now, if you look at what happens in terms of what we're able to measure, this is actually a very important equation in terms of being able to find molar mass. So if you look at molar mass, so let's say, for example, you're going to have methane, CH4, all right? Well, if you look at being able to find, I put an extra C in there, hold on. That's just CH4. So it isn't like, and this is what I've tried to stress to you, it isn't like we can put CH4 underneath a microscope and see the structure of this thing, okay? We can't. So there's a whole bunch of different things that we've got to be able to do to try and figure out what this formula actually is. So one of the keys to this is if you can look at this in terms of molar mass. So we can't directly isolate an individual molecule of this stuff, but here's what we can do, is that we can measure the density of the gas. This is kind of a Dr. Seuss thing. We can measure the density of a gas in a flask. Oh, okay. So we would know here's a certain volume of flask, okay? So we know the volume. We'd inject methane into it, so we would know that density. So then we know the gas law constant. We'd measure the temperature. Oh, we put a pressure gauge on here. We can get the pressure. So these 3 things here, the density, temperature, and pressure, are very easily measured on a macroscopic scale. So if we can measure those, then we can figure out the molar mass of the gas in the flask. Oh, you get carbon, that's 12, plus 4 hydrogens, you get 16 grams per mole. Oh, Now if I know what this is, then that's going to be a huge clue to figuring out what the structure is of that particular molecule. Okay, so here's how you could use something like this. So let's say that I want to find the density of carbon tetrafluoride, CCl4, and I know the pressure is 714 torr, and the temperature is 125 degrees Celsius. So that's it's a pretty stout temperature, okay, 125. It's above the boiling point of water. So I took the 714 torr and converted that into ATMs. The carbon tetrafluoride molar mass is 154. There's my gas law constant. Make sure that you're using the liter atmospheres per mole Kelvin. And here's that temperature in Kelvin. So if you do all the math, you get 4.43 grams per liter. Okay. Now, but here's how it's more important in terms of actually being able to use this in terms of like an actual setting. So we want to figure out the molar mass of a gas, and we know the density, and we know that we're at 31 degrees Celsius, and we know that we have an atmospheric pressure of 0.967. So from this, we're going to try and find this molar mass. So we don't know what the formula is, but if we can figure out what the molar mass is, then that could give us a huge clue in terms of figuring out the actual structure of this. So we've got the density, 3.09, gas law constant, temperature 304. Boom, we got 79.7, if you do the math, as your molar mass. So once you figure that out, now remember, this is going to be the molecular molar mass. So remember, you can also talk about the empirical molar mass. So for example, you might have a simple formula of CH2 and say, oh, okay, right, that would be, the molar mass of this would be 12 plus 2, which would get me 14. So that might be the empirical molar mass. But then, let's say, for example, you know that out of a calculation like this, let's say that you know the molecular molar mass is 28. So if the molecular molar mass is 28 and the empirical is 14, remember this little trick. So I take 28 and divide that by 14, I get 2. So then if I take 2 and multiply that by each of the subscripts, I get C2H4, right? So that tells me the actual structure of the molecule. So I might have one set of data that would give me the empirical formula, and then out of the gas law, I might be able to figure out the actual molecular structure and say, oh, that's C2H4, based upon the molar mass of 28. So in terms of actually being able to figure out formulas, this equation is very, very, very handy to have. Okay, so here's kind of the last big thing, and what's called the law of partial pressure, and it's represented by the Greek letter chi. And basically, there's a couple of ways you can look at this. It's basically like a percentage. So if, let's say, for example, you know the number of moles is 1, and then you divide that by the total number of moles. So, and you can express this as also as N1 plus N2. So if you know the total number of moles in a gas, like let's say it's a combination of, here's a container and you introduce some oxygen and some carbon dioxide, whatever you introduce in here. So then if you know the total number of moles and you know how many moles of the oxygen that you introduce, so that's why I said this is kind of like a percentage. So it's N10 divided by the total number of moles. It's the number of points that you got correct on the test divided by the total number of points that are available on the test, if you want to look at it that way. Now, here's the other way that you can look at this in terms of doing a little bit of creative math. So if you take the ideal gas law, PV equals nRT, and you solve for N, you've got pressure times volume over RT. So I separated this out as a separate entity. So then I'm going to write this as, okay, so I want to look at this in terms of my different numbers of moles. So N1, that number of moles, is also going to equal the pressure created by 1 times volume over RT. Then I can do the same thing with the second number of moles. Oh, okay. That's going to be P2 times V over RT. Oh, okay. Now, so then I'm going to go back to how I began to calculate this whole thing of partial pressures. Oh, here's my partial pressure 1, N1 over N total. So then I'm going to take this idea here and put this in here. So then I'm going to have P1 times V over RT. Then I'm going to have P1 times V over RT plus P2 times V over RT. So then what's going to happen is that I can cancel out my VRTs. And so then I can write this as just as the pressure as well. So if I know that the pressure of a particular gas might be, I don't know, 0.8 atms, and then if I know that the total pressure in the system is 1.6 atm, then I know that that partial pressure then would be equal to 0.5, because if I take 0.8 and divide that by 1.6, that would get me this. Because the reason that it's handy to work in pressure is that we can hook up pressure sensors to the LabQuest and we can measure pressures. We don't have N sensors to measure the number of moles. So that's why it's easier to express this thing in terms of pressures, because that's something that we can easily measure. Now, the other way that you can, if you do some simple manipulation here, so pressure 1, if I move this over here, also equals the total pressure times that partial pressure, which is Z1, or Chi1, excuse me. So let's say, for example, you have this problem. So you know that the partial pressure of nitrogen air is 0.0708. Okay. Or you can think of it as being 78.1%. It's the same idea. So if we know that the total atmospheric pressure in the room is 1.08 atmospheres, and we want to calculate how much of that pressure is created by just the nitrogen, we're just taking that 0.7808, which is just like a percentage, and we're multiplying that by 1.08, and we're going to say, oh, 0.843. So 0.843 atmospheres is created as part of that out of the entire 1.08 atmospheres. So it's just kind of a handy thing to have. So here's what I'm going to do. I'm going to send you a gas assignment, and I'm going to send you the answer key to that. Just do the ones that are circled. You'll see that because those are the ones that are on the answer keys. And this covers a lot of this stuff that we've just talked about. So there's that. And then I've got one more big lecture to get ready on just kind of some catch-all odds and end things, electronegativity and ionization energy and that type of thing. So we'll call